Happy Tuesday. If you haven't seen the email, I believe it was sent out like mid-March, late February about the final. Finals May 4th, 10:15 to 12:15. Also, as a reminder, next Friday we do not meet. It's reading and review day where students are studying for their finals, he says sarcastically, because y'all know what's really going on that day. I will still be here. So I'll still come into this room, same time. I think it was like extended office hours. So I can't cover anything new unless you initiate it. I can't do a review unless you initiate it. So it'll just be you come in and ask questions and I can answer them, but I can't do anything without you initiating it. We are still working on surface integrals. Day 3 of surface. It's day 2.5 of surface integrals. I mean, if you want just a single sheet, that's fine, but it's going to be open notes. Believe on Friday we had just started looking at flux, right? I think we only did one flux problem. There you go. Evaluate, again, assuming positive orientation, evaluate outward flux of the field zx negative 3y squared z through the surface of the cylinder x squared plus y squared equals 16, located in the first octant between z equals 0 and z equals 5. And John's going to do this for us.
Got it. Let's see.
I'd be surprised if it was actually correct. Just looking at it and being able to do that. Remember, we want parameterization of the surface. Parameterization of a cylinder was given. It was derived in the video. Don't remember if I derived that normal vector. So since I'm not sure if I derived that normal vector, I'm just going to do the calculation for this problem to find the normal vector. But that would be the normal vector for a cylinder. Cylinder has a radius of 4. Guess I should clarify that this is if the cylinder is extending up along the z-axis. Right, so the axis of the cylinder is the z. You should be able to see slight modifications for if it's going along the x or the y. Domain. What is our domain? What about z? We all agree?
The first option,
So what does that mean?
the theta would be 0.2.
If we were dealing with the whole cylinder, it would be 0 to 2 pi. And we're specifically in the first octant, that means that x and y have to be 0. So in the first quadrant, theta goes 0 to pi over 2. And then z does extend 0 to 5. Normal vector. We want outward pointing. You have to keep that in mind. Right. Typically, we just say it's the partial of g with respect to the first variable cross partial of g with respect to the second variable. But there's no law that says it has to be theta z. You could write it as z theta, and then you'd have gz cross g theta. Obviously, the only difference between the two is the sign. Right, one's the negative of the other. Until you actually do the cross product, you do not know if that's the order you want. That's the only problem with this. So just pick an order, do it, and make sure that your normal vector points in the right direction. If not, just multiply by -1, and that would be the normal vector you want. Want the partial of g with respect to theta. Well, that's easy. It's not a complicated parameterization. Now the partial with respect to z is even nicer. 0, 0, 1. You can save yourself a lot of work. You're taking essentially a vector in the plane and crossing it with the unit vector in the z direction. Oh wait, I did that wrong. Last component's guaranteed to be 0. I was thinking of multiplying 2 vectors in the plane. If you multiply 2 vectors in the plane, obviously your result is perpendicular, so it's going to be in the z direction only. Right, I don't know how. Yes, I do. So do the cross product. For cosine theta, for sine theta, 0. Now you want to examine that and make sure that that is outward pointing. And since we're only 0 to pi over 2, cosine and sine are both positive, right? So this vector is going to point in the positive x direction and positive y direction. All right, so it's going to be pointing essentially towards quadrant 1, right? Further into quadrant 1. Is that of the cylinder? Yes, it is. Perfect. So this is outward pointing. So that is the proper vector we want. X y squared. Right, remember the flux integral. You have a question? Right, so think of the surface of a cylinder. Right. Try and draw it in quadrant 1. Draw the cylinder first and I'll deal with. Whatever. Good enough for government work. Right? Remember, we're only in the first octant. Right, we just pick a point on the cylinder. I'm going to draw its normal vector from that. So based on the normal vector we have, does it point away from the surface or into the surface? Well, for us, it points away. So that is an outward pointing normal vector. Right, so you can think of it like it's radiating away. The normal vectors are radiating away from the surface. That would be outward. If it's being pulled in, that would be an inward. Evaluate flux, right? It's the double integral over your domain, over the parameter domain. Evaluate the field over the parameterization. Right, so Z becomes Z. X becomes 4 cosine theta. Y becomes -3. Y becomes 4 sine theta. And I think it was what? Z, right? Yeah. And just Z again. I am going to actually rewrite that. 4 squared is 16. 16 times 3 is 48.
Why isn't zero? Or I'm sorry, why isn't Z just zero?
Because that's the normal vector, not the parameterization.
Oh, wait, yeah. Okay.
I mean, based on that observation, when you do the dot product, it's really not going to matter what that last component is it? Because it's going to go to 0 anyway, but setup is important. Now ds becomes the normal vector ds, or dA rather, right? I'm not going to have enough room. Let's first just evaluate that dot product, see what we get. First term, 4z cosine of theta. Second term, 16 cosine sine. And of course, the third term is just 0. Can factor out of 4. I think I am going to do that. Factor out of 4 from 16, you're left with 4. But sine theta, cosine theta is a half sine of 2 theta. Just so I don't have to worry about U sub, I'm just going to do that as half sine of 2 theta. Don't have to. I'm going to say there is the first setup. All right, so that's the setup to evaluate the flux integral. Now the setup to evaluate the double integral. And the order, it doesn't matter, right? dz d theta or d theta dz. Sadly, we're not integrating over one full period of either cosine or sine 2 theta. So we can't just simplify it that way. We actually do have to do the work. Z squared over 2 from 0 to 5 is 25 halves. Right, that second term didn't have a Z in it, so it's just going to be that term times the length of the interval. Antiderivative cosine is sine. Sine evaluated from 0 to pi over 2 is 1. Antiderivative sine of 2 theta would be negative a half cosine 2 theta. Now, cosine of 2 theta from 0 to pi over 2 is the same as cosine of theta from 0 to pi, which is negative 2. That's 4 times 45 halves, which is 2 times 45. Outward flux is 90. We want to evaluate the outward flux of the curl field of that given vector field for the portion of the sphere x squared plus y squared plus z squared equals a squared that lies above the xy plane. Now this is just evil. If we had it, this problem would be a lot easier with Stokes' theorem. But we don't. So I have to do this the hard way. First, let's find the curl. Partial y. For the last component minus partial z of the second component. I'm just going to write that as x because it's 2x minus x. Partial z of the first component. Bless you. Minus partial x of the third. Oh no, sorry, y. Partial x. Minus partial y, which is 1. Left with negative 2z. So there's our curl field. Parameterization of the sphere. A cosine theta sine phi, A sine theta sine phi, A cosine phi. Right? What's the domain?
Theta is from. And then 5 would be. Does everyone agree? For what? Why pi over 2? Oh, wait, because it's split in half. Okay.
All right, we're dealing with the upper hemisphere, right? Noma vector has been derived. It is a nasty derivation. Very tedious. Radius squared times sine of phi times the parameterization of the unit sphere. You may see me get lazy. whereas G sub 1 or S of 1 just to represent parameterization of a unit sphere. Which, by the way, I can write G as A times S of 1, which I might do if it's beneficial. Right? Or I could just write that. Do if it's beneficial. Right? Or I could just write that as S of A to represent parameterization of sphere of radius A. Either way, right? Because that is very messy to write. I don't think it really benefits me in this problem. Late with style. Like it. Because you have style, I'm not going to make you come up and finish this problem.
I was looking at it on the team.
I saw you. Yeah, I saw you. All right, so double integral over D of our curl field, which is actually a very nice curl field. Dotted with our normal vector. This is where I'm probably just going to write it shorthand just because I don't feel like writing that long thing. Oh, wait a minute. I need to rewrite that curl field. That needs to be evaluated at G. I don't feel like erasing and redoing, so I'm going to do this. Evaluated over G. Curl field evaluated over G would just be that. So close to the parameterization of a sphere of radius A. If it wasn't for that bloody 2, this would be a very nice problem. It's from the curl. Except that shouldn't be negative 2z, should it? Oh, yeah, it is. So that should be a -2, not a +2. That's an easy fix. That there should be negative. Right, it's from when we took the curl. Now we get to do the dot product. Gonna make life slightly simpler. Can factor out an A. And remember, when you do dot product, if you have scalar multiples, you can take the scalars, multiply them together, and then do the dot product of the remaining vectors. We're going to get an A cubed. And A is constant, so factor it out. Gonna have a sine phi common. That's from there. Now we have to do the dot product. Remember, S1 is the parameterization of the unit sphere. So first component's cosine theta sine phi times cosine theta sine phi. There's our dot product. This can be simplified. We have a cosine squared theta sine squared phi plus a sine squared theta sine squared phi. Isn't that first term just sine squared phi? Distribute that sine phi through, you get sine cubed. Minus 2 sine of phi cosine squared phi. That can technically be simplified. Can factor out a sine phi, you'd have sine squared minus, oh wait, that 2 there, never mind. That's a problem. Doesn't matter if that 2 wasn't there, the simplification wouldn't help. So there's the setup as a double integral. Well, the good news is there's no theta. Theta. this problem is evil. That second term, straight up change a variable. That's not too bad. That first term, however, if you were to do that by hand, two ways you go about it. You could do integration by parts. It's not the path I would take. You would have to split that as a sine times sine squared, rewrite sine squared as 1 minus cosine squared, and then do change a variable there. Let u be cosine. I'm just going to use formula number 22. Formula 22 gives us sine cubed antiderivative negative 1/3 times quantity of 2 plus sine squared times cosine. And then clearly, that second term is going to give you 2/3 or negative 2/3 cosine cubed phi, but of course it's already minus, so it becomes plus. Evaluated from 0, pi over 2. At pi over 2, cosine is 0. At 0, sine is 0, but cosine is 1. The first term will evaluate out to a simple 2/3. That second term evaluates out to minus 2/3. You do all of that work and it's 0. Welcome to physics. That's 90% of physics problems, which makes us happy. We want stuff to go to 0 in physics. Still sucks. Again, that does not mean that there is no flow through the surface. It just means that the net outward flow is 0. So inward and outward flow would cancel out. Or there could just be no flow through it. I don't know without actually plotting it. Gonna find outward flux 4xz minus y squared and yz through the surface of the unit cube. Within a unit there. Less than a unit here. No. Okay. Uh-oh, that's not what I wanted to do. Where's my zoom view? No. I think that's what I had. Those connect. These two should also connect. Oh, they do. Perfect. All right, so that would be, I guess, a rough estimate of the unit cube. Not done. So I want this. There's our unit cube. Now, of course, because I'm using technology, I can just move that and say I knew exactly how much space I needed and did it perfectly my first try. So we want flux through the surface of this cube. How many facings does a cube have? That means we have to do 6 flux integrals. 1 for each facing. This problem is a bad word. This is kind of like that path integral we did of a square, right? Where we had to do 4 separate path integrals. Yeah, we need a parameterization for each of the 6 facings. Started. Let's start with front facing. The circle dot. Doesn't matter what you use to represent it. Parameterization. Be 1yz, wouldn't it? Remember, this point right here is the origin. Because it's the cube 0, 1, 0, 1, 0, 1. X pops out of the screen at us, so this would be 1 for X. I'm going to write it this way for the domain. Both Y and Z would go 0 to 1. Right, I can even simplify that even further. A common notation you might see is that to represent that both Y and Z are between 0 and 1. I'm going to call this the back facing. The only redeeming quality of this problem is that the parameterizations are actually very simple. Right, so for the front and back facings, your X is a constant, isn't it? For the front, X is 1. For the back, X is 0. Y and Z both vary from 0 to 1. Well, the other 4 facings are going to be similar, right? You're going to have your 2 side facings where your Y is going to be constant, and then X and Z can range from 0 to 1. Then you have your top and bottom facings where your Z will be constant and your X and Y will range from 0 to 1. So the facings at least have simple parameterizations. right facing. And left. And then there's your top and bottom. Normal vectors. Start with the front. Remember, we want outward pointing. Well, if we just imagine this screen, just imagine it as our cube. That'd be the normal vector. Front facing. Strictly in the x direction, isn't it? Specifically, the positive x direction. Just I hat. For the back facing. Well, now just imagine that that was the back of the cube. Be negative I hat, wouldn't it? The right facing, right? The arguments are going to be the same. You're going to have j hat. And then the left facing would be negative j hat. Top facing is k hat. And the bottom facing would be negative k hat. There's the 6 parameterizations with their normal vectors. By the way, such a surface is called a closed surface. A sphere is a closed surface. Right. So closed surfaces have no boundary. Hemisphere is not closed. It has a boundary. That circle on the bottom is its boundary. Again, I'm not going to write out field. So the flux over S. And since S is closed, we will often write that. Much like you did with path integrals when the path was a closed path. We wrote the surface as the union of non-overlapping surfaces. So the total surface integral would be the sum of the individual surface integrals. Or in our case, the sum of the 6. Front. Right, we're evaluating our field along here. And then we're going to dot it with I hat. Well, this is simple then. If you dot a vector with I hat, it's only the first component that you get, isn't it? Because I hat is 1, 0, 0. So all we have to do is look at the first component for the front and the back. Evaluate that component only at the parameterization, and we get 4z. It's going to do minus because it's negative I hat. This time, though, x is 0. Same argument with J and K. For J, all we have to do is evaluate the second component at the parameterization. Oh, well, the second component's negative y squared. And then the K components, we just want the third component, right? Z is 1 and 0 respectively, and it's YZ. Just because of how our vector field was defined, 3 of the surface integrals are 0. Now that is nice. And look how simple the other 3 are. Oh my goodness, that one is so nice. Four Z is 2Z squared. From 0 to 1 is 2. Minus 1. Plus. Y squared of 2 from 0 to 1 is 1/2. We get 3/2. This problem was nice only in the sense that the field was nice and the cube they gave us was positioned nicely.
How do we get four Z dz dy for the front base?
So look at the field. You want to evaluate that over the parameterization, right, which is 1yz. And then you want to dot that with I hat. Right, so dot it with I hat, you only care about the first component. So you can imagine how hideous these can get. Cube had 6 facings. Pyramid has 4. How many facings does a dodecahedron have? A lot. If it was a closed surface integral, you'd have to do this process. That is a bloody nightmare. This is the motivation for divergence theorem, which gives us a way of simplifying closed flux integrals. The closed path integrals is the motivation for Green's theorem. Gives us a way to simplify that. I don't know what the motivation of Stokes' theorem was. I just think Stokes was a devil. Because, oh my God, it's awful.
I had a question going back a little bit. For the first integral that we set up, where it's 4z dz dy, where did we get 4 from? Or I guess 4z.
First component of the field.
Yeah, we actually had like a whole.
Yeah, there was a field there. Yeah. By the way, we can now look at the integral forms of Maxwell's equations. They deal with surface integrals and path integrals. And so all 4 of Maxwell's equations have 2 forms: a differential form using divergence and curl, and an integral form using line integrals and surface integrals. So glad I'm done with surface integrals. Questions on surface integrals? And depending on your major, yes, you're going to be seeing them a lot. Physics, I can guarantee you, you're going to be seeing a lot. Pretty sure electrical engineering is also going to see it a lot. Right, because the biggest use of flux is in flow of electricity through a surface. Electric flux, magnetic flux. Maybe Mechie? Depending on what you're doing. I don't think civil sees it. But of course, if you're civil, you already know what the engineers say about you.
Yeah.
So, yeah. Although I think a new field took over that. I think there's now a new engineering field that's looked down on more than civil
Yeah.
within the engineering field. Bio?
Is this engineering?
There's a business engineering?
Yeah, that's that. Yeah, it's like stupid. It's all about like so.
That probably doesn't even count. They don't even probably count that as engineering in the engineering field. Probably just look at you and go, "You're not an engineer. Get the hell out of here." Business. Okay. There. So on Thursday, we're going to start the three big theorems by looking at Green's theorem, which gives us a way of doing a closed path integral as a double integral. And trust me, depending on the closed path, you want to do it as a double integral. Right? It basically alleviates you needing to break it down into multiple paths. See you Thursday.
So do we need to come in for the final in our, or is it an online submission?
I have not decided yet. I'll have a
Okay.
decision next week.
And I was wondering, are you proctoring a class at RCBC?
Proctoring?
Or I saw
I
your
teach
name.
that class.
Are you teach it? Are you doing like, I saw.
I have two
online,
classes. I have
online.
differential equations and Calc 3
Yeah,
over the summer.
I might have to take differential equations.
And it's gonna just be converted from the differential equations I'm doing this semester there.
Okay, and it's like weird, there's no Zooms or anything.
It's completely online.
That's
As
terrible.
a distance learning.
Yeah, well,
Well, I had 6, 2 dropped out. The remaining 4 are all doing pretty well.
that's good.
So differential equations luckily isn't really. It sounds a lot worse than it really is.
Do you ever like meet with your students, like if they ask, or is?
Yeah, you can still schedule office
Okay.
hours.
Okay.
That's fine.
Yeah, I found an in-person linear algebra class at RCSJ, so that's the only one I could find in person.
Yeah, there's stuff to do.
Yeah.
I've done it. It's not easy. Well, it's easy to me.
Yeah. Not for.
Not easy to learn it, especially if you're not used to rigorous mathematics and it's your first look at it. And now you get to do it all by yourself. Have fun. You too.
For the final, is it like they covered like after test 3 or like?
Well, there's going to be a 4th test. Yes,
Okay.
and then the final's comprehensive. So it's going to cover the entire semester. Your tests. I don't create one, but your tests would be a good resource, and the quizzes.
Also, so good testing the quizzes.
Yes, they would probably be really good resources.
Do them well and understand.
Yeah,
them
we-
really
If
good.
yes, so so I'll put it this way: my finals. The people who fail the finals weren't going to pass the course to begin with because they didn't put in any effort. So if you do well on the tests and the quizzes, you're going to do just fine on the final. It's nothing to panic about. So don't panic.
Oh, so the quizzes and the tests.
Yes, those are really good resources. Now, it does come from a different test bank. I do use a different test bank for the final than I do for the tests. But, I mean, all test banks are generally written the same way, so yeah, as long as you can do well on that, you'll be fine. Don't worry about it.
Thank you.
Professor,
So I wanted to, I'm pretty sure these guys asked the same question, but I want to ask about the final. So is it in person and are